Hello. So we've looked at different ways in which energy can be stored and some different energy transfers as well, how it can move between stores. So just to clarify, if you're not quite up to speed with those definitions, can't quite remember from last lesson, different ways in which energy is stored, I'm talking about gravitational potential energy, kinetic energy, thermal energy, those sorts of things where energy is stored. And energy transfers, I'm talking about, well, maybe the chemical energy stored in a candle will be transferred into thermal in the surroundings because of a chemical reaction. Or maybe the kinetic energy of something sliding really, moving really fast across the floor, eventually slowing down, that kinetic energy will turn into thermal energy, and the reason for that is friction, the force of friction. And you can imagine sliding your hand over your other hand, and there's going to be this frictional force that means the kinetic energy, the movement energy, will turn into thermal energy. So done quite a lot of stuff on that. Now we're going to look in detail at different energy stores. And these energy stores, well, energy's got like a value. We can say, they're 10 joules of energy, right? We can put energy on, maybe something else has got 20 joules of energy, it's got more energy. So we're going to be using equations, to work out how much energy is in each store. And we're going to start with, we're not going to do that for all of the stores, we're going to do them for some choice stores that are on the specification. We're going to start with gravitational potential energy. So let's imagine I've got this object, I've got this pen, and the pen, I've lifted it up from the table, and it's got some energy stored. It's got gravitational potential energy stored. If I let go, that energy store is going to turn into kinetic. When it hits the table, it will turn into thermal energy, maybe via sound, but it will warm up the pen, warm up the table a very small amount. When it's up here though, it's got gravitational potential energy, and if I want to work out how much gravitational potential energy it's got, then we're going to use a formula. If I want to increase the amount of gravitational potential energy that this pen's got, I can lift it higher. It's now got more energy. If I let it go, just before it hits the desk, it's going to be going faster than if I let it go from here. So up here, it's got more gravitational potential energy. So in our formula, we're expecting height to be in the formula. The higher you lift it, the more energy it's got. We're also expecting, actually, something else to be in the formula. We're expecting mass to be in the formula. I've also got this. I'll just grab this from the table. It's my kitchen table. I've got this trivet thing, this cast iron thing that you put hot pots on. Really heavy. So if I hold this here, and I've got the pen here, which one's got more energy? Well, actually, the thing with the heaviest thing's got the more energy, and it's actually got, we call it the mass. It's got more stuff in it. So then the mass of this object means it's got more gravitational potential energy. If I let this go and I let this go, then this is going to transfer more energy into my foot if I drop it on my foot, and it's going to hurt. Whereas the pen is going to transfer less energy onto my foot if I drop it on my foot, and it's not going to hurt. So we're expecting, you might be expecting weight to be in the equation, but actually in physics we like to use mass. And that means that also we've got something else that's going to be in our equation, because if I was on the moon and I lift this pen, I don't know what this is, 40 centimeters above the desk, 40 centimeters above the table, it's going to have less gravitational potential energy than if I was on Earth. Right? If I drop this, if I let's go back to this, if I drop this on my foot on the moon, it's not going to hurt as much as if I drop it on my foot on Earth. So the gravitational field strength we're also expecting to be in the formula. So I'm just going to show you the formula. This is our formula for gravitational potential energy. If we want to find the gravitational potential energy that an object has, and the standard symbol for that is EP, which will save us time in an exam because we don't want to be writing all of this, then we can multiply the mass of the object, but it has to be in kilograms, otherwise the energy won't come out in the standard unit, which is joules. It will come out in some crazy units and you're not going to know what they are. So we need to make sure everything here is in standard units. So if we get our mass in kilograms, we multiply it by a gravitational field strength, which on Earth is 10. in the exam, they'll tell you that though, so you don't have to remember that on Earth it's 10. They'll tell you in an exam, gravitational field strength. On different planets, it'll be different again, but you don't have to remember this value. And they multiply that by the height, and the height has to be in meters. And this means, if you think about this equation, if I've got something that's got more mass, so my trivet for putting hot pots on, more mass than the pen, so more gravitational potential energy. If I lift it up higher, then it's going to be, H is going to be larger, so it's more gravitational potential energy. And if I have increase the gravitational field strength, maybe I go to Jupiter and keep everything else the same, then that's going to be more gravitational potential energy. So we've got this equation that seems to make sense to us. You do have, for your exam, have to remember it, but we're not going to get bogged down with remembering it now. We'll do that when we've got quite a few equations, and we'll use a Littner card system with those equations that we've got. So we're not going to try and remember it now, but you do have to remember it for your exam. And we're going to try and start using standard symbols. So you might not like this. You might prefer to see it written as gravitational potential energy equals mass times all in words, but that takes ages to write out. And when you get to your exams, you're not going to want to spend that time writing it out. If you're asked to write down this formula, or you're asked to use it in your workings, you don't want to write all of these words out. So we just use these standard symbols, and after a while, we'll get to know what these standard symbols are. So M for mass, we always use M for mass in our equations. So there is an element of just getting used to it. Another thing I'll say about this is that you might like to put time signs in your equation. That's bad algebra, so I don't do it, but actually in your AQA exam, the examiner doesn't care at all. So if you're more comfortable with putting time signs in here, you're more than welcome to. So we're going to use this equation now for a little practical. We're going to work out the gravitational potential energy that you get from walking up the stairs. And then we're going to work out the gravitational potential energy you can give an object by lifting it up onto a table. We're going to use our gravitational potential energy equation for a little practical. The practical is going to be the amount of gravitational potential energy you gain by walking up the stairs. That's what I want you to work out. And then the amount of gravitational potential energy you gain by lifting up an object. So we're going to do those two things. First up though, in our equation, so we've got gravitational potential energy equals mass times gravitational field strength times height. In an exam, they always tell you gravitational field strength. It's 10, I'll tell you now, on Earth. It's 10 newtons per kilogram of the units, but they'll tell you that in an exam. So it's just a number. The mass though, your mass, you're going to need to work out using some bathroom scales. And if you haven't got any bathroom scales, then you can assume that you're 80 kilograms. Let's go for 80 kilograms. And then we're going to also need to measure the height of the stairs. But once we've done that, once we know our mass, we know gravitational field strength, G, and we know the height of the stairs, then we can work out the energy that you gain by walking up the stairs. So these are my bathroom scales. I'm going to stand on them. So I have got a mass then of, brilliant is it, 86 kilograms, let's go for 86 kilograms. So I'm going to use 86 kilograms in my, okay, so these are my stairs, and I'm just going to measure the height of this stair. So this stair, ruler's upside down, and you won't be able to see this because I've got a steel, you might be able to, but a difficult ruler to read anyway. The stairs are 20 centimeters tall, and if I know how many stairs I've got, then I can work out how high they are. So 20 centimeters tall for one stair, so 2 stairs, that'd be 2 times 20, it'd be 40 centimeters tall, and so on. I am gonna walk up the stairs and count how many I've got, and then multiply 20 by how many stairs I've got to find the total height of my stair. 5, 6, 7, 8, 9, 10, 11, 12, 13, one around the corner, 14. I've got 14 stairs then. So the height of my stairs is 14 times 20, which is 280 centimeters. So that's 2 meters 80. We need to have it in meters because meters is the standard unit for length. So get your height of your stairs in centimetres and then convert it into metres. And it should be fairly similar to mine. I've got a house with tall ceilings, so it's probably going to be lower than that. And if you live in a bungalow, then you have to find some steps outside, and you're probably going to find just maybe like 3 or 4 steps, and that's not going to be anywhere near this much, but you can still do the experiment. Okay, so the formula that we're using is this. Gravitational potential energy, mass, gravitational field strength and height. And the mass, my mass was 86 kilograms, and kilograms is a standard unit of mass. And the height of my stairs was 2.8 meters. So to find and I also know that gravitational field strength is 10 newtons per kilogram. So I should be able to work out then now the energy that I gain by walking up the stairs. Whenever I walk up the stairs, it'll be 86 times 10 times 2.8. Okay, and then I would just type this into a calculator and press equals, and that is my energy that I gain every time I walk up the stairs. I'd like you to do the same for your stairs and your mass. If you haven't got any bathroom scales to find out what your mass is in kilograms, then assume that you're 80 kilograms. All right, why not? Second experiment then, I want to work out how much energy I need to lift up a can of Coca-Cola from the floor to the table. So to do that, I need to know the mass of the can of Coke. I need to know gravitational field strength, which again is 10 newtons per kilogram, which they'll give you in an exam, and the height of the table. Now, I've got a tape measure, just got this one it's a sewing type tape measure actually, but a steel one for DIY type stuff would work just as well, if not better. If you haven't got anything to measure length that's longer than a ruler, then you'll only be able to lift your object, and it doesn't have to be a can of Coke, it could be anything. You'll only be able to lift your object sort of 30 centimeters using a 30 centimeter ruler. But if you've got a tape measure and you can measure the height of your table, that is what I'd like you to do. My table is 77 centimeters high, so you can see that there, the zeros down the bottom. 77 centimeters is 0.77 meters. We have to have everything in meters because it's a standard unit of length. So that's the height of my table. And this can of Coke has a mass of, now this is in grams, 358 grams. Grams is not the standard unit of mass. So I want this in kilograms. And in kilograms, this is 0.35, it's changed, but 0.358. So those are my values. And then every time I lift the can from the floor to the table, I'm going to work out how much energy I'm giving the can. So once again, my formula is energy equals mass times gravitational field strength times height. I've just missed out the time signs because it's bad algebra, but if you put them in, that's fine. If it makes it clearer for you, then that's a good thing. The mass of my Coke can was 0.358 kilograms. We'll have to have everything in standard units if you think back to that first lesson that we did after Christmas. Gravitational field strength is 10 newtons per kilogram again. And the height of my table was 0.77 meters. Remember, this needs to be in meters. It's a standard unit of length. So if I'm going to calculate the energy that I need to lift up my Coke can from the floor to the table, it will be 0.358 times 10 times 0.77. So again, I'm not going to work that out, but I just type that into a calculator and press equals. I wouldn't expect it to be very much. It'll be a couple of joules, if that. The units for energy, of course, is the joule. So whatever value I get should be a capital J afterwards for joules. But I would like you to do a similar thing for your table or something similar, and your object, which is an object like my Coke can, but could be anything really. So good luck. I'm sure if you've got any problems with this, then let me know and I'll see if I can solve them. But yeah, that's what I'd like to do. Thank you.